Hello everyone. So today we are going to discuss basics of lighting system which will be useful in this course. So under lighting system we will discuss about radiometry, photometry and colorimetry. So before going to further discussion, let us understand the electromagnetic spectrum. So as you see here, the electromagnetic spectrum starts from gamma ray, shorter wavelength, and they are of high frequency and higher energy. And then you have X-ray, and then you have ultraviolet spectrum, and then you have the visible part of the spectrum here, and then you have the infrared IR, and then microwave and radio. So as we move, it is a longer wavelength, lower frequency, and lower energy. So this particular course, basically we are going to discuss communication in either in visible region or IR region or ultraviolet. So we'll limit ourselves to this part of the spectrum. So let us now first understand radiometry. Radiometry is the detection and measurement of light waves in optical portion of the electromagnetic spectrum, which is further divided into ultraviolet, visible light and infrared. So this is a typical radiometer, and if you see the output of a radiometer, it looks something like this. You have the wavelength on this side, and you have the percentage of light for that particular wavelength in that part of the signal. So this is the basic definition of radiometry. Under radiometry, you have different quantities. So first one is radiant power. So assume Q is your radiant energy. Then the radiant power is defined as dQ by dt. That's a radiant power, and it is denoted as phi E. And the units are in watts. So this is radiant power. The radiant intensity is defined as it is defined as IE dQ over solid angle. So basically it tells you how much light is falling onto the surface defined by this solid angle. So that is called as a radiant intensity, and the units are watts per steradian. And the third quantity is irradiance, which is EE. This is the amount of light, amount of radiant energy falling onto a surface of unit area. And this is defined as dQ over dA. And the units are watts per meter square. The third quantity is the radiance, which is denoted by LE. This is defined, suppose you have a source here, this is a source, and this is your surface, and some light is falling onto some area here, for example here, and this is your detector, could be I, for example, or it could be a photodiode or some sensing material. So this light which is falling onto this eye or any sensing material is called as radiance. So the unit, it is how it is defined. It is defined as dQ over dA d omega, and the units are watts per meter square steradian. So these are the 4 quantities which are useful, and these quantities come under radiometry. So this is a definition of solid angle. Suppose there is a point source, and then this is the dA area on the surface of the sphere, and then for a point source the solid angle is defined by A by R square, where A is the area and R square is the radius of the sphere. So this we will be using in, when we are analyzing optical wireless communication system. Sometimes it is easy to assume point source, so that mathematically you are able to solve, and you are able to get good insight of the problem. So the second part is photometry. Photometry is actually a subset of radiometry. All light measurements under radiometry is a special subset weighted for a typical human eye response. So as we see in this diagram here, you have the wavelength here, and this is a percentage of light which is sensitive to human eye, and human eye responses to this particular set of wavelength. So we can say this is a weighted or scaled version of radiometry with respect to human eye response. So similar to radiometry, we have different quantities in photometry. First one is luminous flux. The symbol is phi and the units are lumen. It is denoted as Lm. And the second quantity is luminous intensity. The symbol is I and it is lumen per steradian, or also this is known as candela. So first let us see the luminous intensity here. So the lumens per unit solid angle in this case is called as luminous intensity, and the units are, as I mentioned, is either lumen per steradian or candela, denoted as CD. The third quantity is illuminance, which is represented by E. This is the light falling onto a surface, and the units are lumen per meter square, and this is also called as lux. So this is also lumens per meter square is also called as lux. The fourth quantity is luminance, which is represented as L. The units are candela per meter square, which means the light falling from a source in some solid angle d omega, and from the reflected surface, from the surface it is reflected and it is collected by the eye, and that part of the that part of the light is called as luminance, and as you change the position of the eye, this luminance might change. So this is the basic parameters which are used in photometry: luminous flux, luminous intensity, illuminance and luminance. So in order to understand this more, so this is a source of light where you have luminous flux which are called as lumens, and then the light falling in a particular solid angle is called as luminous intensity or candela, and then it falls onto a surface. So the area which is reflected, the light which is reflected from the surface is called as illuminance. The units are lumens per meter square, and then it is collected by the eye, so which is called as a luminance, and the units are candela per meter square. So let us just briefly understand about the history of photometric units. So the first definition of one candela is, the luminous intensity of a standard candle, which is a very vague definition. So it is now obsolete. The second definition is 1 centimeter of platinum at 2042 degree which is a temperature of solidification, has a luminous intensity of 20 candela. So this is another standard. Again, this is an obsolete, very difficult to measure this. The third definition, which is the current definition and which is an accurate definition, is you use a monochromatic source of light source, which has a power of 1 by 683 watt at lambda is equal to 555 nanometer into a solid angle of 1 steradian, then the luminous intensity will be called as 1 candela. So I'll repeat the correct definition of candela, that you use a monochromatic source which has a power of 1 by 683 watts, and the lambda 0, the wavelength is 555 nanometer, and it falls, and you're measuring in a solid angle of 1 steradian, then it will give you a luminous intensity of 1 candela. So there are different regimes. This I am referring to basically the visible part of the spectrum. So it is divided into two parts, the regimes. The photopic regime, where you have good amount of light, or it is a well-lit situation. For example, outdoors, sunny, or in a store where a lot of lighting is there, or early twilight. So these are all examples of photopic regime. And then you have another regime which is called as scotopic regime, where there is very less light. It is poorly lit. For example, there's no moon or it's overcast. So that is called as scotopic regime. And the light which is in between is called mesopic regime. So basically there are three regimes depending upon whether the situation is well lit or poorly lit or somewhere in the middle. Now, as you know, the eye has two types of photoreceptors. One is cone, other is rod. So cone is sensitive to photopic regime, where the light intensity is high or is a very lit environment. And the rod are sensitive to scotopic region, where the light is very less. And these are some values of scotopic region, less than 0.003 candela per meter square, and mesopic lies between 3 and 0.003 candela per meter square, whereas the photopic vision region is greater than 3 candela per meter square. And if you see the eye sensitivity of the human being, and this is as per the CI 1931, this is a standard. So it has different luminous efficiency for photopic and scotopic. So the blue line here is actually photopic, and this red line which you see here is scotopic. And on this side you have the wavelength. So you have different sensitivity experienced by the eye for photopic and scotopic region. How do you convert a radiometric quantity to photometric quantity? So this is the power spectral distribution of the source, which is PE lambda, and this is V lambda, which is eye sensitivity function. And then when you multiply and integrate from 380 to 780, which is the visible range, and there's a constant here, there's a constant here, then you can get photometric units. So this is eye sensitivity function. It could be both for photopic or scotopic, and this is the power spectral distribution, and this is constant. So if you do this integration, you get the photometric quantity, corresponding photometric quantity. So this is another way of explaining for both the regions, luminous and radiant powers. So the relationship is You have luminous power as phi V. V stands for visual. This is some constant, and this is some radiometric radiant power, which is phi E. And then if you have the photopic vision, then this constant is actually Km into V lambda naught. Whereas for scotopic is a different constant Km prime and V prime lambda, as we had discussed in the earlier graph. V lambda 0, that is eye sensitivity function, is different for photopic and different for scotopic. So V lambda and V dash lambda are for photopic and scotopic, and then Km and Km dash, they are the constant, and this is how you get the value of K lambda naught and K dash lambda. And then you, for the photopic vision, the equation becomes phi V, which is the luminous power, 683 lumens per watt. This is a constant, which is, Km here, and lambda 0 is over the visible range, and this is your phi E is your radiant power into eye sensitivity function. D lambda 0 gives you the value of luminous for the photopic. Similarly, we can find out for the scotopic vision, where the constant is different. It is Km dash, which is 1700 lumens per watt, and then this is also eye sensitivity function is also different, which is V dash lambda 0. So this particular slide basically tells about the luminous efficacy and luminous efficiency. So there are various light sources, combustion, which includes candle, incandescent, light emitting diode, arc lamp, and so on and so forth. So basically, let us consider on the light emitting diode, because this is the one which we are going to use during our discussion in optical wireless communication system. So these are the typical values of a light emitting diode. So suppose I take a white LED here. Then the luminous efficacy, which is actually lumens per watt. That means if I have 100 watt of source or 100 watt of source, it will give you, say for example, 1000 lumens. Then the luminous efficacy is 1000 by 100, which is 10 lumens per watt. So this is how the luminous efficacy is described, and this ranges from 4.5 to 150. There are some sources which have got much better luminous efficacy. So we are looking for such sources which are good for illumination, as well as they will be used for communication. That we will see later in forthcoming lectures. And this is the luminous efficiency. This is actually expressed in percentage. So the amount of light which is produced by the source, not everything comes out. For example, in LED, inside the LED, lot of photons are generated, but ultimately, some percentage of the photon comes out. So basically, this is defined as luminous efficiency. That is, and the units are in percentage. So for a typical LED is of the order of 0.66 to 22%. And the loss is because of some absorption happening and for example, in light emitting diode, not everything is converted into radiative recombination. There are some non-radiative recombination, so there is some loss. There is some loss because of reflection and things like that. So basically, whatever you get actual output is much less than what it is produced in the fixture, which actually it is defined by the term luminous efficiency. These are some of the illumination values which are as per IES standards. So this is given in terms of foot candles. So let us understand what is a foot candle. So 1 foot candle is nothing but 1 lumen per feet square. And this can be converted into 10.7639 lumens per meter square, which is actually equal to 10.7639 lux. So 1 foot candle is roughly equal to 11 lux. So that is a very approximate way of relating foot candle and lux. So for example, in a parking area, for example, or halls or aisles, typical you require 5 to 10 foot candles, or in terms of lux, it will be 50 to 100. For example, if you go to the other extreme, in a fine bench where you are working on a minute, equipments, or very, very difficult inspection areas, then the luminance which is required is about 2000 to 5000 lux. So depending upon the situation, whether it is some stairways or it is some drafting room or some reading fine print and things like that, so this illumination criteria changes. So this is some of the typical values of illumination, because as we will see that we are going to use the current LED which are mounted inside the room or inside the office for communication. But ideally those LEDs are mainly for illumination, giving this much amount of lux. So same power I need to use for communication. So that is why these things will be relevant when we discuss the communication part of it. Another thing which we will frequently encounter is a Lambertian source. So what is a Lambertian source? Lambertian source, the brightness or the luminance is independent of angle. That is L theta is equal to L naught. So whatever the theta, the value is constant. Whereas the intensity falls as cos of theta. So this is a very approximate representation of a source. Not all source will meet this criteria, but to make it more mathematical friendly, we normally take source as Lambertian source. So I theta is equal to I0 cos theta. Intensity is falling off as cos theta, as it is clear in this diagram. So the intensity here is I0, and as at an angle theta, it is I0 cos theta. So most of the LEDs which are there, they are nearly Lambertian surfaces. Now let us now come to colorimetry. It is a field of science that deals with the assessment and the quantification and the measurement of color as it is perceived by the human eye. So as you know, there are three basic colors: red, green and blue. So you can produce any color using R, G and B. And the wavelength for red is 700 nanometer, for green it is 546, and for blue it is 435. So now I want to convert this any color into some sort of coordinates. We'll see whether you require 2 coordinates or 3 coordinates, but right now suppose these are the tri-stimulus values, X, capital Y and capital Z is actually the power of the source scaled down by visual response of the eye, which is X lambda 0 here. This is for a particular color, say for this may be for say R. Similarly, this Y tri-stimulus value is for say G, and this is for B. And this corresponding XYZ chromaticity coordinates are given by X is equal to X divided by X plus Y plus Z, and so on and so forth. And if you see here, if you add these things, they become 1. So basically I need only 2 quantities. Once I know X and Y, the Z can be found out. So basically I want to translate any type of color into XY coordinates. So that is what this color matching function and chromaticity coordinates does. So this is a transformation between X, Y, Z, this tri-stimulus values, and red, green and blue. So they are related in this fashion, and these are the X, Y, Z. So Z, one of the quantity is not required because we know X plus Y plus Z is equal to 1. So basically we require just two components, X and Y, and X can be represented in terms of some constant into the R, the red component, the green component, the blue component, and similarly Y can be represented in terms of R, G and B. So this is a typical color matching function, XYZ color matching function. So basically there are two standards, 1931 and 1978. 1931 is adopted in most places and quite accurate. But here for comparison, both the standards have been given, but more or less they overlap. So these are the X, Y and Z function, which I call them as color matching function. They are represented here, and on Y axis you have the wavelength. So finally what we get CIE XYZ chromaticity diagram. So here in this diagram you see these are the X coordinate and these are the Y chromaticity coordinate, and on the edges you will see the monochromatic light here. As you move towards the center, this color saturation actually is decreasing. This color saturation is decreasing as you move to the center, and in the center where you have all the components of X and Y and Z, you get actually white light. So this is a white light region here, and there are different shades of white light, and this is the point of same energy, that is this black point which has 1 by 3, 1 by 3, 1 by 3 for both R, G and B, and basically if you have equal energy point or equal contribution of RGB, you will get white light of this, which is defined by this point, particularly this point. So this kind of analysis will be used in communication, where we will be using this diagram. For example, in RF we might have heard of constellation diagram. So different points or signals are represented by different constellation diagram. Here also we will represent the different constellation points using some combination of RGB, and we will try to make a group of constellation diagram which will be used for modulating the input signal. So that part is called as color shift keying, that we will discuss in detail at a later point. But this diagram will be useful when we discuss a color-based modulation scheme.